7 minutes ago, an alert went out that nobody in the astronomy community was ready for. Not a supernova, not a comet, not a routine data dump from another exoplanet survey. A signal, a structured repeating signal, picked up by the James Webb Space Telescope, pointed directly at the TRAPPIST-1 system, 40 light years from where you're sitting right now. If you're just joining us, welcome, because today, August 14th, 2026, might end up being a date you remember. Not because we have all the answers, we don't, but because for the first time in a long time, one of the most powerful telescopes humanity has ever built may have caught something it wasn't supposed to catch. Let that sink in for a second. TRAPPIST-1 isn't just any star. It's the system that broke the internet back in 2017 when astronomers announced not one, not two, but 7 roughly Earth-sized planets orbiting a single dim red dwarf star. 3 of those planets, TRAPPIST-1e, F, and GE, sit inside what scientists call the habitable zone, the Goldilocks zone, the not too hot, not too cold, just right for liquid water zone. Ever since that discovery, TRAPPIST-1 has been the single most watched planetary system outside our own solar system. Every major telescope, with the sensitivity to look, has looked. And James Webb, the most advanced space observatory ever launched, has spent years quietly staring into that system, sipping starlight, trying to figure out if any of those 7 worlds actually have atmospheres. So when word started spreading that Webb had logged something anomalous, something the automated pipelines flagged as statistically strange rather than routine noise, the reaction inside the space-watching community was immediate. Not panic, not aliens-confirmed headlines. Something more interesting. Careful electric curiosity. The kind of curiosity that comes from serious people trying very hard not to get ahead of the data. Here's what we know, and I want to be upfront that "know" is doing a lot of work in that sentence. Webb's instruments, specifically the kind of spectrographs used to split incoming light into its component wavelengths, are built to detect incredibly faint patterns. When starlight passes through or reflects off a planet's atmosphere, certain wavelengths get absorbed by certain molecules. Water vapor absorbs light differently than methane. Carbon dioxide leaves its own signature. Oxygen leaves another. This is called transmission spectroscopy, and it is, quite literally, how we've been trying to read the chemical fingerprints of worlds we will never physically visit. What reportedly came through in this latest observation window wasn't a clean chemical signature. It was something stranger. A repeating pattern in the data stream that didn't immediately match known atmospheric noise, known instrument artifacts, or known stellar activity from the star itself. And if you know anything about red dwarf stars like TRAPPIST-1, you know that's a big deal, because these stars are notoriously messy. They flare, they spike, they throw off radiation in ways that make clean signal detection incredibly difficult. Scientists have spent years building models just to filter out TRAPPIST-1's own tantrums from real planetary data. So when something shows up that doesn't fit the flare model, doesn't fit the noise model, and doesn't fit any previously cataloged instrumental hiccup, that's the moment researchers sit up straight. Now, I want to pause here because this is the part where a lot of channels would just start yelling aliens and cut to dramatic music. We're not doing that. Not yet. Because here's the truth about how real science works. Anomalies get investigated, not announced. Extraordinary claims, especially ones involving the possibility of extraterrestrial technology or artificial signals, require an extraordinary level of verification. Scientists call this the burden of proof, and rightfully so, because history is full of signals that turned out to be satellites, microwave ovens, or faulty cables. But here's why. This one is different enough to talk about. TRAPPIST-1 isn't a random patch of sky. It's arguably the best real estate in our galactic neighborhood for finding life as we understand it. 7 planets, 3 in the habitable zone. Tidally locked worlds where one side may bake in eternal daylight while the other freezes. In eternal night, creating strange twilight bands around each planet's equator where temperatures might sit just right for liquid water to exist. If there was ever a system where researchers expected something eventually, it's this one. And that's exactly why this moment matters so much, regardless of what the signal ultimately turns out to be. Because right now, in real time, we are watching the scientific process happen. The flag gets raised, the data gets pulled, teams around the world start cross-checking, peer review begins, skepticism gets applied, hard, relentless skepticism, because that's what real discovery survives. If it holds up, it's history. If it doesn't, we learn something about our instruments, our models, or our star. Either way, right now, today, on August 14th, 2026, something got Webb's attention. And if you're watching this, you're getting the story as it's unfolding. So stick with me, because in the next section, we're going deep. how James Webb actually detects something like this, what signal even means in a scientific context versus a sci-fi context, and why the TRAPPIST-1 system has been an obsession for astrobiologists for almost a decade now. Section 2. How do you even hear a signal? 40 light years away? Let's slow down for a second because I think a lot of people picture this moment like something out of a movie. A giant satellite dish, a room full of scientists in headphones, someone whispering, "We've got something." That's not really how this works. And honestly, the real version is even more incredible. James Webb doesn't listen for radio signals the way SETI, the search for extraterrestrial intelligence, does with giant radio telescope arrays here on Earth. Webb is an infrared telescope. Its job is to capture light, specifically infrared light, which is essentially heat radiation wavelengths just outside what human eyes can see. Every star, every planet, every warm object in the universe gives off some amount of infrared radiation, and Webb was engineered with an almost absurd level of sensitivity to pick that light up from unimaginable distances. So when we talk about Webb detecting a signal, we're not talking about a radio broadcast, a beeping Morse code pattern, or anything resembling the wow signal that radio astronomers famously picked up back in 1977. We're talking about a pattern in light data, brightness fluctuations, wavelength absorptions, timing irregularities that doesn't match the models scientists have built to predict what normal should look like. Think of it this way. Imagine you know a song so well you could hum along with your eyes closed. You know every beat, every pause, every note. Now imagine one day, in the middle of that song, there's a note that shouldn't be there. Not louder, not necessarily even noticeable to someone who doesn't know the song. But to you, because you know the pattern so intimately, that one note stands out like a scream in a silent room. That's essentially what happened here. Webb has been staring at TRAPPIST-1 on and off for years. Astronomers have built incredibly detailed models of what normal looks like for this star, its flare patterns, its brightness cycles, the way its light dims slightly every time one of its 7 planets crosses in front of it during what's called a transit. These transits are actually how most of what we know about TRAPPIST-1's planets was discovered in the first place. Tiny, precise dips in starlight as each world passes between the star and our telescopes. So when the data comes back, showing something that doesn't fit any of those established patterns, a wavelength dip that repeats at intervals nobody predicted, or a timing signature that doesn't match any known planetary transit, that's the note that shouldn't be there. That's what triggered attention today. Now here's where I want to bring in some real context, because this moment doesn't exist in a vacuum. TRAPPIST-1 has been a magnet for anomaly hunting before. Back when Webb first started analyzing TRAPPIST-1c and TRAPPIST-1b in the early 2020s, researchers found something almost disappointing at first glance. These inner planets appeared to have thin or non-existent atmospheres, likely stripped away by the star's intense radiation over billions of years. That was a real result, published, peer-reviewed, and it cooled a lot of the early hype around the system. But the outer planets, E, F, and G, sit further from the star's radiation blast zone, and they've remained the most tantalizing targets precisely because we still don't have conclusive atmospheric data on them. Every observation window Webb spends on those planets is treated like precious, limited resource because Webb's time is shared among thousands of research proposals from scientists all over the world. Getting Webb pointed at TRAPPIST-1e, F, or G isn't easy, and it isn't cheap in terms of telescope time. So when something unusual comes out of one of those windows, it gets noticed fast. This is also where I want to address the elephant in the room, because I know some of you are already thinking it. Could this actually be a technosignature? A technosignature is the term scientists use for a sign of technology, something like an artificial transmission, an unnatural light pattern, or a structure that couldn't occur through natural processes alone. It's a real legitimate field of study, and serious researchers, not just fringe theorists, have built entire careers around designing systems that could detect exactly this kind of anomaly. The honest answer right now is nobody serious is claiming that's confirmed. Not today. What we do have is a flagged anomaly that doesn't fit existing models, which is genuinely rare and genuinely exciting, but doesn't fit the model, covers a huge range of much more mundane possibilities, an unaccounted for stellar flare, an instrument artifact, a cosmic ray hit on the detector, background contamination from a much more distant object lining up in the field of view, or even a data processing error that hasn't been caught yet. Every single one of those has happened before with Webb data, and every single one of those gets investigated before anyone announces anything close to a genuine discovery. But here's why it's still worth your attention, even in the most boring case scenario, where this turns out to be an instrument quirk or a modeling gap. We learn something. Webb's entire mission depends on scientists refining their models every time reality throws them a curveball. Every anomaly, confirmed alien signal or not, makes the next observation sharper, the next model more accurate, and the next real discovery more likely to be caught the moment it happens. And in the best case scenario, however unlikely, we're witnessing, in real time, the earliest moments of what could become the most significant discovery in human history unfold in front of us today, August 14th, 2026, on a channel you happen to be watching right now. So don't go anywhere, because in the next section, we're breaking down exactly what happens next. How a flagged anomaly turns into a confirmed discovery, who actually makes that call, and how long we might realistically be waiting for real answers. Section 3, from anomaly to announcement. What happens next? Okay, so a strange signal gets flagged. What actually happens after that? Because I think this is the part most people never see, the unglamorous, methodical, sometimes agonizingly slow process that separates a real scientific discovery from a viral rumor that fizzles out in 48 hours. First thing that happens, the raw data gets pulled by the team that actually had observation time allocated on Webb for TRAPPIST-1 during this window. Nobody just sees an alien signal pop up on a public dashboard. Webb's data typically goes through a proprietary period where the scientists who proposed and won that observation time get first access, specifically so they can do exactly this kind of verification work without a global feeding frenzy interfering before they have even confirmed what they're looking at. Second, the anomaly gets run through what's essentially a gauntlet of boring explanation checks. This is the part nobody puts in the headline, but it's the most important part of the entire process. Scientists ask, is this a cosmic ray hit? Cosmic rays are high-energy particles that occasionally slam into Webb's detectors and create false readings that look, for a split second, like real data. Is this a known instrumental artifact? A quirk in how one of Webb's 4 main instruments processes light under certain conditions? Is this stellar activity from TRAPPIST-1 itself, which, remember, is a notoriously flare-happy star? Is this contamination from a background object? A much more distant galaxy or star that happens to sit in the same tiny patch of sky? Every single one of those explanations has to be tested and ruled out, one at a time, using both automated analysis software and old-fashioned human scrutiny from experienced astronomers who've spent careers learning what normal weird looks like versus actually weird. Third, and this is critical, independent replication. In science, one team seeing something once is interesting. It is not proof. The gold standard is getting a second completely independent team, ideally using different instruments, different analysis software, and different assumptions, to look at the same target and see if they find the same thing. This is exactly what happened with the famous WOW signal from 1977, and it's part of why that signal, despite being incredibly compelling, was never confirmed as artificial. It was detected once by one instrument and never repeated, despite decades of follow-up attempts pointed at the exact same patch of sky. So if today's TRAPPIST-1 anomaly is going to go anywhere, the next real milestone isn't a dramatic press conference. It's quieter than that. It's other observation teams requesting priority time on Webb or on ground-based observatories to point instruments at TRAPPIST-1 again and see if the pattern repeats. If it does, even once, that changes everything. If it doesn't, and this was a one-time blip, it likely gets logged, studied, published as an interesting anomaly in a technical journal, and quietly folded into humanity's ever-growing catalog of weird things space does that we still don't fully understand. I want to be really clear about something here because it matters. Even NASA and the international teams that operate Webb move through official channels that are almost aggressively cautious when it comes to anything resembling a potential biosignature or technosignature. There's a real historical reason for that caution. Science has been burned before by premature announcements, moments where excited researchers or media outlets got ahead of the data, only for the discovery to quietly dissolve under further scrutiny. Nobody wants to be the team that cried alien. That caution is actually the whole point, and honestly, it's what should make you trust this story more, not less. If today's anomaly turns into nothing, that's the system working exactly as intended, filtering out noise before it becomes a false headline. And if it turns into something real, the fact that it survived that level of scrutiny is exactly what will make the eventual announcement credible, instead of just another viral space rumor that gets quietly deleted a week later. So what's the realistic timeline? Here, historically, anomalies like this, and when they do get resolved, take anywhere from a few weeks to several months to move from flagged in the data to published finding, depending on how much follow-up observation time is available and how complex the analysis turns out to be. Webb's schedule is booked incredibly far in advance. So even if a team wants to immediately repoint the telescope at TRAPPIST-1, they may have to wait for an open observation slot, unless this is treated as urgent enough to warrant what's called a director's discretionary time allocation, essentially a fast-tracked priority observation, window reserved for exactly this kind of we need to check this right now situation. If that happens, if Webb's schedule gets shuffled specifically to re-observe TRAPPIST-1 in the coming days, that alone would be a massive signal, no pun intended, that the people closest to this data think it's worth taking seriously. So here's what I'd watch for, starting today, August 14th, 2026, and in the days that follow, announcements of any expedited or priority Webb observation time pointed at TRAPPIST-1, any statements, even cautious ones, from the research teams involved, and any preprint papers uploaded to open access science servers where researchers often share early findings before formal peer review completes. That's usually where the real story breaks first, quietly, long before it becomes a headline. In our final section, let's zoom out and talk about why this moment, regardless of how it resolves, says something much bigger about where we are as a species in the search for life beyond Earth, and why TRAPPIST-1 specifically has become ground zero for that search. Section 4. Why this moment matters, no matter how it ends. Let's zoom all the way out for a second, because I think it's easy to get lost in the technical details and forget just how wild this moment actually is, even before we know the ending. 40 light years. That's the distance between us and TRAPPIST-1, to put that in perspective. The light hitting Webb's mirrors right now, carrying whatever information triggered today's anomaly, left that star system around, the year 1986. It has been traveling, uninterrupted, through the vacuum of space for 4 decades, just to reach a telescope humanity finished building and launched into orbit less than 5 years ago. Whatever caused this anomaly, a stellar flare, an instrument quirk, or something genuinely unexplained, happened decades before most of you watching this video were even born. That's the part that never stops being surreal to me. We're not looking at TRAPPIST-1 as it is today. We're looking at a 40-year-old postcard from a star system, and today, August 14th, 2026, is simply the day that postcard happened to arrive with something written on it that nobody expected. And here's the thing. Even if this specific anomaly turns out to be nothing more than an unusual flare or a modeling gap, the fact that we're capable of having this conversation at all is genuinely remarkable. 20 years ago, we didn't even know TRAPPIST-1 had planets. The system wasn't even on astronomers' radar as anything special until 2016 and 2017, when a relatively small ground-based telescope survey first spotted the telltale dimming patterns that revealed not 1, but 7 roughly Earth-sized worlds orbiting a star smaller and cooler than our own sun. That discovery alone rewrote how astronomers thought about planet formation around red dwarf stars, which, by the way, make up the vast majority of stars in our galaxy. If red dwarfs like TRAPPIST-1 can host multiple rocky, potentially habitable planets, the math on how many potentially life-friendly worlds might exist across the Milky Way shifts dramatically upward. That's why every single observation Webb makes of the system, anomaly or not, carries weight far beyond just TRAPPIST-1 itself. It's a test case, a proving ground. If we can learn to reliably detect atmospheres, chemical signatures, and yes, even genuine anomalies around TRAPPIST-1's planets, we're building the exact toolkit we'll need to study potentially thousands of other similar systems in the years and decades ahead as next-generation telescopes come online after Webb. I also think it's worth sitting with the emotional weight of this moment for a second, because I don't think enough space content actually does. There is a very real chance, small but real, that within our lifetimes we could receive the first genuinely credible evidence of life, or even intelligence, beyond Earth. And if that happens, and it probably won't happen the way movies have trained us to expect. There won't be a dramatic first contact scene. There won't be a single unmistakable message. It will probably look exactly like this: a flagged anomaly in a data stream, buried in spreadsheets and light curves, examined quietly by exhausted researchers, double and triple checking their work before they dare say anything publicly. The most important discovery in human history might not announce itself with fanfare. It might just be a note that doesn't fit the model. So where does that leave us today? Honestly, in the best possible place a story like this can be, right at the beginning. We don't have confirmation. We don't have proof of anything beyond a flagged anomaly that scientists are now working to explain. But we have something almost as valuable: a front row seat to how real scientific discovery actually happens in real time, with all its caution, rigor, and deliberate refusal to jump to conclusions. If this turns out to be nothing, we will have learned more about how to interpret Webb's data and how to model TRAPPIST-1's behavior, which makes the next real discovery easier to catch. And if this turns out to be something, Even something modest, like unexpected atmospheric chemistry, rather than anything resembling a technosignature, it would still represent one of the most significant exoplanet findings in the history of the field. Either way, mark today's date, August 14th, 2026, the day James Webb caught it. A note that didn't belong in the song 40 light years away, in a system that has captivated scientists for nearly a decade, and the day we started watching together to find out what it means. Make sure you're subscribed because the moment new information drops on this story, and it will, we'll be breaking it down here first, with the same care, the same skepticism, and the same excitement we brought you today. Stick around. This one might just be getting started,